The explosive birth of atoms, how the universe forged everything around you. Everything we touch, breathe, and see is made of atoms. Richard Feynman, one of the greatest theoretical physicists of the 20th century, once said that if only one piece of scientific knowledge could be passed on to future generations, it should be this: everything is made of atoms. This simple idea carries within it the foundation of all matter. But to understand how atoms came to be, we must dive deep into the very beginning of the universe, when time and space themselves began. Atoms are not just tiny bits of matter. They are intricate structures with a dense center called a nucleus, made of protons and neutrons, and surrounded by even lighter particles known as electrons. Each proton carries a positive charge, each electron a negative charge, and neutrons are electrically neutral. In a stable atom, the number of protons equals the number of electrons, balancing the charges and leaving the atom overall neutral. The simplest atoms in the universe are hydrogen and helium. Hydrogen has one proton, no neutrons, and one electron. Helium has 2 protons, 2 neutrons, and 2 electrons. While Earth is full of many other elements like carbon and oxygen, across the universe, these 2 simple atoms dominate. Scientists group atoms by elements, determined by the number of protons they have. Every atom of carbon has 6 protons, every atom of oxygen has 8, and so on. So when did the first atoms appear? The vast majority of hydrogen and helium atoms formed about 400,000 years after the Big Bang, the moment the universe began around 14 billion years ago. At that time, the universe was still about 1,000 times smaller than it is now and much hotter. So hot, in fact, that electrons couldn't settle into stable orbits around atomic nuclei, they had too much energy. The universe had to cool down to roughly 5,000 degrees Fahrenheit, or 2,760 degrees Celsius, before electrons could finally be captured by protons and neutrons, forming complete atoms. This process, which occurred during a stage misleadingly named recombination, marked a turning point. It allowed light to travel freely through space and atoms to begin forming the matter we recognize today. But the nuclei of helium and a heavier form of hydrogen called deuterium were created even earlier, just minutes after the Big Bang. At that time, the universe was still more than 1 billion degrees Fahrenheit. Only in such extreme temperatures could protons and neutrons collide with enough energy to stick together and form stable nuclei. This early phase of the universe's history laid the groundwork for what would become nearly all the normal matter we know, about 90% of it in the form of hydrogen and another 8% as helium. Still, there's a problem. You and I, along with all plants, animals, rocks, oceans, and planets, are made from atoms far more massive than hydrogen and helium. Where did these heavier elements come from? The answer lies inside stars. To build atoms larger than helium, you need conditions that are both hot and dense, conditions found at the heart of stars. Inside these stellar furnaces, nuclear fusion drives protons and neutrons close enough for a fundamental force known as the strong nuclear force to bind them together, forming heavier atomic nuclei. The temperature in these stars often exceeds 1 billion degrees Fahrenheit, the same scorching conditions that existed only minutes after the Big Bang. Stars heavier than our Sun are especially capable of forging elements ranging from carbon all the way up to iron. These stars spend their lives slowly building heavier and heavier elements through fusion, using the immense energy generated to shine for millions or billions of years. But even the most powerful stars can't form atoms heavier than iron on their own. That's because these larger atoms are unstable and require extra energy to hold them together. For them to form, something far more violent must occur. That's where supernovae come in. When a massive star exhausts its fuel, its core collapses in a matter of seconds. The result is a titanic explosion, a supernova, that releases an enormous amount of energy. In those brief moments, temperatures and pressures surge high enough to forge atoms heavier than iron, including nickel, copper, and even uranium. These elements are then flung into space, enriching the surrounding galaxy and seeding future generations of stars, planets, and eventually life. Even more exotic cosmic events, like the collision of neutron stars, pushed the limits of atomic creation further. When two of these ultradense remnants slam into each other, the resulting explosion is so powerful it creates massive amounts of heavy elements, gold among them, before collapsing into a black hole. These collisions are among the most extreme phenomena in the universe, and scientists are only beginning to understand how important they are in forming the heavier atoms we find on Earth. So while hydrogen and helium emerged from the early universe, the rest of the periodic table, the carbon in our bodies, the calcium in our bones, the iron in our blood, and the gold in our jewelry, was forged in the hearts of stars and the violence of stellar death. The atoms that make you were once part of stars that exploded long before Earth even existed. To grasp how atoms came to be, one must understand the basics of nuclear physics, particle interactions, and a touch of general relativity. But even with all this knowledge, the universe still holds secrets. There exists something beyond ordinary matter, dark matter. It doesn't interact with light and seems to be made of something entirely different from atoms. Scientists still don't know what dark matter is made of or how it formed, but they are working to find out. Ultimately, the story of atoms is the story of the universe itself. From the scorching moments after the Big Bang to the fiery death of stars, the formation of atoms connects the cosmos to us. Everything we are, everything we build, and everything we dream, begins with these tiny building blocks, born in fire, scattered by explosions, and gathered again into something as complex as life.